Hey, this is Avi Gutman with another Ask Me Anything event brought to you by quantreasoning.com. I invite you to join me live next time. We do this every Saturday at 11 a.m. Eastern, and you can attend for free by starting your free trial at quantreasoning.com. So I'm going to start by asking you all with this really long and wordy word problem. Can you identify where is the first place that it would make sense to pause and digest and maybe even make some kind of inference? Perfect. Exactly. And so what would you do, Joseph, at that point, either with pen and paper or in your head? Like what kind of work, what kind of thinking would you do there? That is a very good instinct. And what is that relationship? How would you put it down on paper? Perfect. Let me put that down here. So we have day 1 and we have day 2 and we have OJ, water, and orangeade. We know these ratios. In day 1 it was 1 to 1 for a total of 2 because we were mixing these two things together, and once we've mixed them it would make sense that the quantity is the sum of the individual quantities, because that's how I think that's from physics, right? It's the law of conservation of matter or something like that. I'm translating from Hebrew, so I'm not sure that that's how you say it in English. And then on day 2 we have, for the same amount of orange juice, we have twice as much water for a total of 3 ratio units. I'm just putting myself in the shoes of the person who is making and selling this orangeade, and I'm thinking, why would I do this? Well, I guess water is cheaper than orange juice, so I'm effectively diluting the orangeade. I'm literally watering it down. So that's what we're doing here on day 2, I guess, to increase our profitability or something like that. So the words the same amount are very important here. That's the reason why we can say that this ratio unit here and this ratio unit here have the same scale factor, essentially. Practically speaking, we could now say, if we wanted to just focus on this column, we could now say, thanks to the words the same amount, we could say now that the amount of orangeade we have on day 2 is 3/2 as much as the amount of orangeade we had in day 1. What I'm doing is I'm reading this ratio from the bottom up and saying we have 3/2 as much orangeade on the second day as we did on the first day. And we're able to make that inference between the rows. I mean, normally you would just make an inference between the columns. In this case, I'm making an inference between the rows, and I'm able to do so thanks to the words the same amount. So that's what enables me to do that. Now, I don't know yet that this is a good and important inference to make, but I'll start suspecting that it's a good inference to make when I read the next sentence. When I stop at this next period, it looks like this is centering around the orangeade. It seems like the orange juice and water were just means to an end. And really the interesting thing here is the orangeade, because we're selling it. And when you sell something, there are a few things that might come up. The price at which you sell it, the cost that it cost you to make it, the profit that you make from selling it, so that would be the difference of revenues and costs. What else could come up? Quantity, right? How much of this orangeade am I selling? So all these different things could come up after this sentence. So this sentence is an important sentence in that it's orienting me towards what this question is probably going to be about. And at that point, I'm really focused on this column on the right-hand side because it seems like that's the thing that the question is interested in. So now I keep reading. If the revenue, okay, so no surprise there. I was expecting something about revenue to come up. If the revenue from selling the orangeade, let's pause there again. The revenue from selling the orangeade would be, how would one compute that? That would be the product of quantity, amount of orangeade sold, multiplied by the price per unit. So however many units we're talking about, multiplied by the price per unit, that would be the revenues. So I'm just kind of digesting what I'm reading and doing some thinking there. And so now I keep reading again. So the revenue was the same for both days. I find that surprising. Because why would the revenue stay the same when my quantity on day 2 is 3/2 as much as it was in day 1? I mean, all else being equal, I would have expected the revenues to also be 3/2 as much on day 2, because if you sell 3/2 as much stuff, then your revenues should be 3/2 as much as well. They're directly correlated. So the only reason I can think of why the revenues didn't increase by 50% or get multiplied by 3/2, however way you want to think about it, we must have lowered our price per unit on day 2. It's the only possible explanation. Now, since this is a multiplicative story, meaning revenues is the product of quantity times price, if I know that the quantity is 3/2 as much, I would need the price to be 2/3 as much, the reciprocal, in order for the revenues to stay the same. And just as a side note, as usual, hopefully you know this by now, my purpose here is not to just get to the right answer. My purpose is to learn as much as we can from this problem that we could apply in other problems and in harder problems. And so that's why I'm solving it as conceptually as possible. This is not the only way to get to the right answer, but in my opinion, it's the only way worth using when you're studying for the GMAT at home. So I made an important inference at this point, right before the word and my inference is that my price on day 2 must be 2/3 as much as it was on day 1. So now I keep reading. If the orangeade was sold at 60 cents per glass, there's my price per unit for day 1. Pause again. What can I infer? The price on day 2 would have been 2/3 of that. So what's 2/3 of 60? That's 40. So I know now that the price per glass on day 2 was 40 cents. That's my inference at that point. All right, let's keep reading. What was the price per glass on the second day? So you see, when we take a lot of time to read and digest and think about a long word problem, when we get to the question mark eventually at the end, when we get to the question mark, either we already have the answer at our fingertips, or the question was too hard for us. Those are the only two options. So if we believe that it couldn't possibly take more than 2 minutes to make our way to the question mark, which I think is fair. Like I can't imagine spending more than 2 minutes just reading the question and thinking about what we were reading. So if that's true, then we would never spend more than 2 minutes on a word problem. Because when we get to the question mark, either we have the answer at our fingertips, so we pick it and move on, or we don't have it at our fingertips, so the question was too hard, and we guess and move on. But either way, we are not spending over 2 minutes on a question. And I think that's one of the most important things that the people need to understand about this test, is that if you can't solve it in 2 minutes, then it's too hard for you, or your approach was bad, right? So the approach that most people would have, this question pops up on the screen, they see that it's a ton of text, and they immediately go into speed reading mode. They try to get to the question mark as quickly as possible so as to have the time to do the math, because they're thinking it's a math test. So they'll spend, if they have 2 minutes for the question, they'll spend 12 seconds getting to the question mark, and then they'll think, okay, now I have 1 minute and 48 to do all the math, but they're confused at that point. They can't make heads or tails of the story and of what the question is asking, and they don't know where to start. So either the approach is bad if you don't have an answer at 2 minutes, or the question is too hard for you, which we're hoping will happen a lot at the test center, because it's an adaptive test. So that's another thing. This is the psychology of the test, right? This is one of the only tests in the world where you go in hoping that a lot of the questions will be too hard for you. That's the hope. And if all of the questions feel really easy, then either you're about to score in the high 700s or you're about to score way below your true ability level. I don't know, 400 or something like that, because you must be making careless errors and picking trap answers without realizing it. And then the difficulty level never goes up, and then all the questions feel easy. Let me just add here on the slide the thinking that we did there. So we had eventually, right, we had day 1 to day 2, and we're comparing them as a ratio, right? So you've got your price per unit, you've got your quantity, and the product of those things is the revenues. And we're told that the ratio of revenues day 1 to day 2 is just 1 to 1. It's just the same revenues on both days. And we made an inference that the quantity was 3/2 as much in day 2 as it was in day 1, or the way I wrote it here, 2/3 as much in day 1 as in day 2, however way you want to write it. And therefore, right, what times 2/3 is 1? Well, this would have had to be 3/2. So now we know that the price on day 1 was 3/2 as much as the price on day 2, or if you want to read it from the bottom up, the price on day 2 was 2/3 as much as the price on day 1, and that was the key inference that we used to solve the question. Just for my own curiosity, can you all let me know in the chat box whether this thing that I have here in the bottom of the slide is helpful to you? Because that's something that seeing visually is useful to you. And notice also how critically important it is to really think about this multiplicative relationship there of price per unit times quantity equals revenues. Okay, good. So there's a consensus here. Everybody finds that helpful. Does this look very familiar to you from reading the word problems chapter of my book? Those of you who have read it? I think it should. I mean, this is kind of the big takeaway, I guess I would say, from the multiplicative stories chapter of word problems in the book. The reason that it reminds you of that is because work is the product of rate times time, just like revenues is the product of price times quantity. And just as an exercise, you might enjoy and benefit from rewriting that question, the orangeade question, as a work rate problem. What would that even look like? We'd have to say something, maybe not with the mixing of the orange juice and water, but start after that. And you'd say something like, the work stayed the same on day 1 and on day 2, but the time it took to do the work was 3/2 as long on day 2 as it was on day 1. And then the inference would be that the speed must have been only 2/3 as fast on day 2 as it was on day 1. So it's an identical question conceptually. And that's why I put all those things under the same heading in the book of multiplicative stories. Whether it's, here's another one, right? The interest that you earn on an investment with a simple annual interest rate is the product of the principal investment multiplied by the simple annual interest rate multiplied by the number of years. That's another multiplicative story. So we have finance, we have work rate, we have speed and distance, because distance is the product of speed times time. We have revenues as the product of price and quantity. We have geometry, right? The area of a rectangle is the product of length times width. All of these things I would put under the same category of multiplicative stories, and this idea of using ratios to solve those questions is really powerful in the GMAT, because almost every GMAT question that includes a multiplicative story can and should be solved this way, abstractly, just looking at the ratios. The only exception would be when the ratios can't be inferred. I think we saw a question like that recently where there was a guy named Don, and he estimated how many hours a job would take, and then based on his regular hourly rate, he said he wanted $336, but then it ended up taking 2 hours longer. It took 4 hours longer than he thought, and therefore his actual hourly rate was $2 per hour less than his usual. And there you can't infer any ratios because all you're getting is differences. So you have a $2 per hour difference, but then what's the ratio of the regular hourly rate and the actual hourly rate? I don't know. I just know one is $2 below the other, but I don't know what the ratio is. And the same thing happened with the hours that it took. He anticipated it would take a certain number of hours. It ended up taking 4 hours more than that, but what's the ratio? I don't know. Because a difference between two tick marks on the number line is not enough to infer the ratio of those tick marks because we don't know where 0 is. And in order to know something about a ratio, we need to know about their distances from 0, right? The ratio is essentially how many times can the distance between 0 and one of the tick marks fit into the distance between 0 and the other tick mark. That's what a ratio is. And a difference between two tick marks doesn't give me any information about where those tick marks are relative to 0. It just gives me information about where they are relative to one another. But 0 could be literally anywhere on the number line, and therefore a difference is not enough to infer anything about the ratio. So that question about Don with the hourly rate is, I would say, the exception to the rule in that you can't, it is a multiplicative story because $336 is the product of hourly rate and number of hours. So it's a multiplicative story, but it can't be solved using ratios because they just gave you the difference in the hourly rate and the difference in the number of hours. So that's the exception to the rule. One way to think about that is, okay, you have two tick marks on the number line. They have some distance between them. In our example, 30 centimeters is the distance between these two tick marks. If you move those two tick marks all the way to the millions, like really far to the right on the number line, a difference of 30 is kind of meaningless. The ratio of the two tick marks, if you're comparing 5 million to 5 million and 30, basically that's a ratio of 1 to 1. Basically. And it's basically the same number. But if you're closer to 0, say you're at 30 and 60, that's a ratio of 2 to 1. That's an enormous difference. And if you're at 1 and 31, that's a ratio of 31 to 1. So the bigger the numbers are, the less of a big deal the gap between them is in terms of thinking of it as a ratio. Hey, I'm just going to interrupt my own video for a moment here. If you're finding value in this video, please let me know in the comments below. And give this video a thumbs up. It really motivates me to keep uploading a new video every day. Alright, back to the video. So before we actually solve this question, there's a little trick that we can use with the answer choices when they're asking which of the following is not a divisor of something. And the only reason I want to go through that trick is because I think it can deepen our understanding of divisibility. So I'm only going through the trick, not really as a tool to use at the test center, but more to just have the conversation, because I think it'll be worth doing so to improve our reasoning. So here's the trick. I want you to all ask yourself the following. So hang on. First of all, I make the observation that I have two answer choices there, A and E, such that E is a multiple of A, right? 35 is a multiple of 7, or if you prefer, you can think of it as 7 is a factor of 35. So that's the important observation that I made. And now I want to ask you the following. If the correct answer is A, just as a thought experiment, if the correct answer is A, meaning 7 is not a divisor of X, what would that mean for answer choice E? If 7 itself is not a factor of X, then 35 is also not a factor of X. And one of the necessary conditions in order for 35 to be a factor of something is that 7 is a factor of that thing. Of course, the other necessary condition is that 5 is a factor of that thing, right? In order for 35 to be a factor, you'd need 7 to be a factor, and you'd also need 5 to be a factor. So if 7 is not a factor, then what chance does 35 have to be a factor? 0. It won't be a factor. So the conclusion from that is then that if A is the correct answer, E is also the correct answer. Now, does the GMAT allow for two answers to both be correct? No. So what can we do based on that? Eliminate A. A can't possibly be the correct answer, because if it were the correct answer, then you'd have two correct answers, and that's impossible. Okay, so again, that's just a trick that's kind of neat, but the important thing about it is the reasoning that it required. So now let's talk about how to actually solve this question. I'm curious, did anybody here come up with prime boxes? So I know that 21 is 3 times 7, and then we also have another 7 threes there, so a total of 8 threes, right? So 3 to the 8, 7 to the 1. That's the prime box of the first term. Now the second term, how would I prime box that? Well, I see that it's a multiple of 4 because it ends with 12, which is a multiple of 4. I'll put a link, once this is a YouTube video, I'll put a link to another video where I go through the reasoning behind that rule. So I'll pull out a factor of 4 there. Let's just put it here on the side. So how many times does 4 go into 112? Well, it goes into 125 times, and then another 3 times to get into the 12 there. So 4 times 28, the 4 is 2 squared, and the 28 is 2 squared, 7 to the power of 1. So altogether we have 2 to the power of 4, 7 to the power of 1. So now we have the value of x in terms of prime boxes, one prime box minus another prime box. And the only thing that we can do when we have an additive relationship between prime boxes is pull out the greatest common factor. I lied, that's not the only thing we can do. There's one more thing we can do, and we're going to do that next. But we'll start by pulling out the 7 as a common factor, like this. The second thing we can do, and this only works if it's a difference of prime boxes, is use the special product for difference of squares. So in this case, we have 3 to the 8, which is some kind of perfect square, and 2 to the 4, which is some kind of perfect square. So I'm going to rewrite this as 7 times 3 times 3 times 3 times 3, that's 81. So I have 81 squared, and this would be 4 squared. So 81 minus 4 times 81 plus 4. We're here. We want it to look something like, and again, that's literally the only move that we have, because these two terms don't have any common factors. And as Surajit noticed, 3 to the power of 8 would be an enormous number, and we just don't have the kind of time, and we don't have a calculator to solve it that way. So then our only move is to make it look like this. So when I see 3 to the power of 8, I think of it as 3 times 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 3. That's what 3 to the power of 8 is. And if I want that to look like this, something to the power of 2, that means that I need to split that in half, essentially, right? To take something that's half the number of 3's. And what is 3 times 3 times 3 times 3? That's 81. So that's how I rewrote 3 to the power of 8 as 81 squared. Our goal is to convert the whole thing to look more like a squared minus b squared. The way to memorize it, because you don't want to just memorize that from a flashcard, the way to memorize 3 to the power of 4 is to think of it as 3 times 3 times 3 times 3, and then say, well, I know that that's 9, and so what's 9 times 9? I know that I already have that memorized. I mean, if you know the times table, then you know that 9 times 9 is 81. So to me, it's a shame to memorize 3 to the power of 4 separately, because now you're not using the stuff that you already know and missing out on an opportunity to make an inference and improve your quantitative reasoning. So I would say if you already know that 9 times 9 is 81, memorize 3 to the power of 4 as 9 times 9. Like, just, reinforce that connection of what 3 to the power of 4 actually is. It's just 3 times 3 times 3 times 3, also known as 9 times 9. Yeah, that's a good comment. I think that most people probably just think that the significance of even exponents is that we don't know which side of the number line the thing started from. If you had an unknown base, say x to the power of 10, oh, 10 is even, so I don't know which side of 0x was. I just know that once it's raised to the power of 10, it will not be negative. But which side of 0 did it start from, I don't know, and then we use an absolute value and the whole thing, right? But you're right, Angie, it's not just that, it's also if we have a difference of things that have even exponents, we can use the difference of squares special product. And yeah, so that's a good comment. So in the end of the day, what is it? It's 7 times 77 times 85. Now at this point, we can either prime box again. I'll do that real quick here. So that's 5 times 17. That's 7 times 11. So I have a total of 7 squared. This is the prime box of x now, right? 7 squared. Oh, let's not forget the 5. 5 to the 1, 7 squared, 11 to the 1, 17 to the 1. That's x. So we could either do that and then start eliminating answer choices, or maybe we just stay at this level of 7 times 77 times 85 and ask ourselves, which of the answer choices can we already tell is not a factor? And I don't know how many of you can tell from just looking at this, but I know that in order for answer choice C to be a factor, x would have to be a multiple of 3, in addition to being a multiple of 5. And I can see that there are no 3's here, because 7 is not a multiple of 3, 77 is not a multiple of 3, and 85 is not a multiple of 3. None of them is a multiple of 3, so I would pick C. If you can't see that yet, then yeah, go ahead and find the prime box of x, and then you'll see that there are no 3's in there, and therefore 15 can't possibly be a factor, and I'll pick that and move on to the next one. The takeaway that I want you all to get here is the following. If you have an additive relationship between prime boxes of very large numbers, you need to pull out the greatest common factor. If you've already done that, and you still have a difference of very large prime boxes, there's only one thing that you can do, and that is what we did here, the special product difference of squares. There's nothing else that you can do. So whenever you are stuck with something that looks like that, right, a difference of two large prime boxes that have no common factors, there's nothing else. There's only this special product. So that would be, I think now that you've seen it, now that you know that, it will be easy to realize that that's the thing to do. Because there's no other thing in the world that you could do. If you found this video useful, go to quantreasoning.com for a lot more where that came from. You should also click that like button and let me know in the comments below what you'd like me to make future videos about. And of course, if you haven't yet subscribed, go ahead and do that and click that bell below so you get notified about future videos. See you next time.